Okay, but before we go into that, uh, in the outline, because we've not really completed a beta function and beta distribution, I'm actually going to start from there. Okay, then from there, I'm going to introduce you to joint probability mass function and joint probability density function. Then I'm going to move into application. But let me first go to beta distribution. Okay, this distribution is actually going to be the last continuous probability distribution we're going to talk about in this class. Now, for you to be able to understand beta distribution, okay, just like gamma distribution, for you to understand gamma distribution, we did a gamma function, right? So for you to be able to understand the beta distribution, we also you need to first understand what we call a beta function. So we use a beta function in a beta distribution. Now I need you to pay attention now. When you take a look at what I have here, okay, that is the integral derivation of a beta function. Okay, integral derivation of a beta function. The range of x has to be from 0 to 1. And you need to have x raised to power alpha minus 1 and 1 minus s raised to power beta minus 1. So that is an integral derivation of a beta function. Okay, now we're also going to have a non-integral derivation. Take a look at that guy. That's a non-integral derivation. As we have integral derivation, we also have non-integral derivation. But let me tell you this, what I'm trying to tell the world now is b comma this, okay, 0 to 1, s raised to power this, 1 minus s raised to power this, the s is the same thing as gamma alpha, gamma beta over gamma alpha plus beta. That's what I mean. What I'm trying to say now, integral derivation is going to be equal to the non-integral derivation. Okay, and you know what? This guy here, we can also rewrite that guy as alpha minus 1 factorial, beta minus 1 factorial, divided by alpha plus beta minus 1 factorial. Okay, please take note of what I'm trying to show you right now. Maybe you given this 0 to 1, s raised to power 10, okay, 1 minus s raised to power 31 dx. Do you know that if you want to solve this problem, you may spend like 500 years solving this problem because of the power. But the fact that the range is from 0 to 1, okay, I'm actually going to call this b of something. Okay, take a look at this. When alpha minus 1 plus alpha, so there's going to be 11, right? 11, comma, okay, 32. Look at that. So this guy is the same as B11, 32. And what is B11, 32? Okay, which is going to be gamma 11, gamma 32 over gamma 43, which is going to be 10 factorial, 31 factorial, 42 factorial. Super cool, right? Very easy to do. It's a calculator now. Okay, so what I just introduced you to now, like I said, we've been talking about beta function, okay, and of course I talk about both integral and the non-integral derivation. Now I need you to take a look at this. We want to talk about every probability distribution as a CDF, right, called cumulative density function. Now for beta distribution, it has an incomplete, look at that, okay? If you take a look at this now, okay, this is the way to write a CDF for a beta distribution, okay? Now, if you take a look at this, it means it's terminating at x, right? Terminating at x. What I'm trying to tell you now, okay, what am I actually trying to say right now? So what I'm trying to say right now Okay, so what I'm trying to say right now is that the probability of x less or equal to x is 0 to x raised to power this 1 minus s raised to power this dx. What I'm trying to tell you is actually this. That's what I mean. Okay, let me be using b instead of I. So b into that, b into that, and this guy is the same thing as this. Okay, so what I mean, this is the same thing as this. Now it's terminating at x. Okay, now if it is terminating at 1, you know, if I go from 0 to 1, if I put 1 here, the whole thing is going to be 1. This is going to divide. This is going to be the same as this. Does that make sense? That's exactly what I mean. Now, what if I put 0? Take a look at it. Look at A. When I put 0, you know what I mean? It's 0 to 0. What's going to happen? 0 to 0. That's going to be 0, right? That's why you have 0. Okay? When you put 1, when I put 1, I mean I want to go from 0 to 1. Going from 0 to 1, okay? From 0 to 1, this divided by this, it's actually going to be 1. Okay? Now, another thing I'm going to show you, please pay attention. Take a look at this. Okay? You know, the high of x, okay, if I'm focusing on x, okay, if I'm focusing on x, okay, I'm actually going to have this here. And if I'm focusing on 1 minus x, which means I want my 1 minus x first. If I have 1 minus x first, I'm gonna switch that as well. That's why you see this. Okay? If I'm focusing on x, it's going to be alpha, comma, beta. But if I'm focusing on 1 minus x, I'm going to switch the parameters. Because if I have 1 minus x raised to power alpha minus 1 is different from what I have here. You know, this one is x raised to power alpha minus 1, 1 minus x raised to power beta minus 1. But if I want to start with 1 minus x, and I want it to carry alpha minus 1, and I want x to carry that, that's a different one. But what I'm trying to say now is that this is the same as that. Okay, so what I'm trying to tell the world is this. You know, what he's trying to say is, if whether beta, alpha, beta, or this, they mean the same. But except that, you know, here, what are you doing? Here, you are actually having this to start. Right? But here, what is starting? 1 minus x is starting. Okay, so 1 minus x, then here is going to be x raised to power this, ds, okay, 0 to 1. So this guy is this guy. Okay, this guy is this guy. Take a look at that. That's what I mean. But they are the same. That's what I mean. Whether b, alpha, beta, or that is the same. Does that make sense? Okay, that's exactly what we mean. Now, take a look at the last one. What this guy is trying to say, when I have alpha plus 1, beta, I'm no longer considering just alpha. I'm adding something to alpha. Then I'm not expecting that to be the same as this. Okay? So it's going to be, this can be expressed as this. What if I ask you, why can't you try and prove this? I'm leaving this as an exercise. If you're able to prove that this equal to that, you can send that to me through my email, and you're going to have an extra credit of 2 points. This, prove that to me. Now that you understand a beta function, we want to go to beta distribution.